If you are currently learning functional programming, or if you're dabbling around with functional programming, but you are still not entirely sure of how to read type signatures, or you want to know more about how to read type signatures, then you're in the right place, because that's what we're going to talk about today. So welcome to another video. I'm glad to be back at the whiteboard. So let me just say before, when I say functional programming, I mean that in a very open sense, whether that's like Haskell or Scala or OCaml, or it's simply that you're hacking around in JavaScript. And I mean, I'm not implying that you need to be hacking around just because you're in JavaScript. I mean, JavaScript is a very fun functional language, and even if JavaScript doesn't have types because it's a dynamically typed language, you might be working with something like TypeScript. And even if you're not working with something like, or I mean, maybe I should say TypeScript or Elm or PureScript or Reason or any of these things that sort of bring types to the JavaScript ecosystem. And even if you're not working with something like that, but you're sort of just using plain JavaScript, or you're using a library like, let's say, Ramda or the Fantasyland specification, or like you're working with something that implements the Fantasyland specification where you still have a dynamic language, totally fine, right? I mean, types still help you to reason about what a particular piece of code actually does, what a particular function actually does. So let's talk about that, right? Like kind of loosely, and let's cover as much ground as possible. So I have this list of things that I want to get through, and whoops, sorry, I left the test text on the board. so I have a list of things that I want to get through, and we'll see if we can manage to get through all of them. And let me just preface this by saying that I'm by no means sort of formally educated in neither category theory nor functional programming, so apologies beforehand if I get some of the terms wrong. Maybe you excellent people who actually know entirely what you're talking about, maybe you could correct me if I happen to be wrong in the comments, so that I'm not sort of leading you astray. But I'll try my best to sort of be specific and just sort of give you an understanding, like pragmatically, of how to read type signatures and how to think about them. So let's just dive straight into it. So these are the things that I want to talk about. I have this cheat list so that I'm not actually forgetting anything. So what I want to talk about are these different things. So I want to talk about this notation. Sorry, maybe that's a bit small. So this colon notation. I want to talk about arrow. I want to talk about squiggly arrow and fat arrow. And I think that's it, right? Fat arrow, squiggly arrow, arrow. Yeah, okay, I guess lowercase letters, right? Yeah, but let's say so lowercase letters. So let's say A, for example, here. I mean, that's just an example. Yeah, I think that's going to be enough to give us sort of a solid understanding of how to read types. So let's just dive into this, right? Like let's assume that we have some kind of type signature, like for example a type signature for the method or for the function add. So it might look something a bit like this. So you might have the function add, like the name of the function is add, and it might map from, let's say, number and number. We're going to look at a bunch of different ways. Number, sorry if I can't spell correctly, to number. Wow, I can spell. But I guess, yeah, I guess that's in screen, right? So the function is called, let me change the colors here actually, right? So the function is called add, right? That's the name of the function. That's the name of the function. And then you have this. Let me actually add some parentheses here. So depending on whether you're in a language that supports multi-arity functions, like if you're in Haskell, for example, you don't have multi-arity functions. So when I say arity, it's the number of arguments that a function or a method. So in Haskell, everything is a one argument function. And there's good reasons for that, because everything in Haskell is curried, because they want to sort of use the power of partial application. Now, we're not going to talk a ton about currying and partial application, but I'll sort of hint as towards the, towards what it is and how you can use it. But I have some other videos on currying and partial application, so do sort of search through my channel if you want to know more about that. It's some really good stuff, and if you're not already familiar with currying and partial application, and you're interested or you're sort of intrigued by the idea of functional programming, get into it. Get into currying and partial application, because it will like literally change your programming world. It's too awesome. Like, it's one of these things where when you've learned it, you will just, like, when you're in a language that doesn't have currying natively, or when you don't when you don't have one-arity functions that you can partially apply, you'll just be frustrated, right? Because it's too good. Okay, but that's a side note, right? So if you have multi-arity functions, then you might have some kind of syntax like this, right? Where you have some arguments here, and then you have some return type here. So maybe here I should say return, right? Return. Sorry, I meant to say returns. Sorry, let me retype this. Return, right? That's the return type. And here, these are the arguments. Right? Argument 1 and argument 2. So what we're essentially specifying is a function that has this syntax. So let me use JavaScript, right, to define this function. So let's say that we use the const keyword. So we're declaring the constant add, and we're saying that the implementation of add is that it takes some x and then some y, and then it returns x plus y. I mean, that's add, right? It's like the function is called add, and its arguments are x and y, argument 1 and argument 2, and then the implementation is that we're adding up x and y, right? And so this would be the type definition, or the type signature. Sorry, sometimes I'll say type definition and type declaration. This is just me being sloppy. I actually mean type signature, but I've sort of learned to say the wrong thing, so I'm trying to unlearn that, but apologies beforehand, right? So this is sort of the type signature corresponding to this particular function. And you can see how we're mapping this, right? It's like the name add here, that maps to this here, right? That's the name. That's this part maps to this part, right? Const here is completely irrelevant, right? We don't care about whether it's defined as a constant or not, right? That's completely irrelevant for the type signature. The type signature just says that I want to care about this thing add. I want to care about this thing called add, and here's what it takes, and here's what it returns. So that's the name, right? And then these are the arguments, right? So you can take this as a whole thing, right? Where it's like these arguments here, they map to this piece of the type signature. Number, comma, number, right? And more specifically, of course, if I use a different color here, you could say argument 1 here, right, maps to argument 1 here. And argument 1 here maps to, or sorry, argument 2 here maps to argument 2 here. And then the return type of the function is a number, right? That's what we're saying here. Like when you invoke this function and you pass it the 2 arguments that you need, or that it needs, you'll get back something of type number. And that's not actually in here, right? Because JavaScript is a dynamically typed language, so you don't need to specify the return type. Now, if you were in C#, for example, or Java, or like some other statically typed language, I mean, sorry, now I went to object-oriented languages, but let's say you had something like Haskell, for example. I mean, actually, in Haskell, you would also say, something like add of x and y is equal to x plus y. Like that would be an implementation, not the type signature, right? But let's just, I mean, for the sake of exhaustivity or something like that, I mean, the type signature in Haskell would have to be something like this: add, and then this colon stuff, and then number. Well, it's not actually number, but let's say you could add in. Let's say we only define add for integers, right? Then you might say int to int to int. So that's a curried version of the same function. Because and I say curried because notice the reusing of the symbol arrow here, rather than having this sort of parenthesis with 2 things. So currying is this idea of taking a multi-arity function and turning it into a series of one-arity function or single-arity functions. So it's difficult not to get into currying when we're talking about type definitions or type signatures, but I mean, currying is this idea of taking a multi-arity function and turning it into a series of single-arity functions, or taking an sort of n-array, a function that takes n arguments, and turning it into a series of what is that, like unary, I guess? Yeah, unary functions, right? Because unary is a function that takes 1 argument. And it's not entirely relevant for this, Yeah, I mean, so understanding currying and partial application will definitely help you understand type definitions. But if you just want sort of a surface level knowledge, you don't have to dive into that yet. But again, like, I would highly recommend diving into that a bit more. So the difference here in some sense is that, notice the difference between this definition and this definition down here. What I mean is, let's use blue here. So this definition here, or sorry, type signature, this type signature here versus this type signature here. It's like we're saying both of them are called add, and both of them take a first number as the first argument. Here we have integers and here we have numbers, but whatever. I mean, it's like maybe the JavaScript version we could define in terms of integers as well, let's say. So we have int and int, and then here in the sort of Haskell definition we have an arrow, right? But in the JavaScript version we have a comma. So in the JavaScript version, we're saying, like, if you just define the function add as a function that takes two arguments like this, x and y, then if you only supply one argument, then that's not a sensible partial application. That just means that you have a function that was supposed to take two arguments, but you've only passed one. And specifically in JavaScript, I mean, this depends on what language you're in. But if you invoke, let's say, this particular function that we've defined here, right? Const add takes two arguments x, y, and returns x plus y. If you invoke that like this, you would say add, let's say 1 and nothing else. Then x would be 1, but y would probably be something like undefined, right? Because you haven't actually passed that. And then you will be trying to, like, what will happen when you run this code add 1 is that you will add 1 to undefined, which will probably, I guess, give you nan, like not a number, right? And that's an error, and that's like not cool. We don't want that, right? And so partial application is not just for we don't have that just for the sake of avoiding errors, like avoiding nans, for example. But it's actually just that what we could do instead, if you call add and just pass one number, if you only pass the first argument, like if we define the function to have the type, to not have the type here, but to have the type here. So instead of saying it's called add, it takes two numbers and it returns a number, we could instead say it's called add and it takes a number, returns a new function that takes a number, and then returns a number, right? That's the way we interpret this sort of arrow, arrow. So the way we would call that function is that if we call this now, if we say add and apply that function to 1, then we'll get back a new function that expects another number. So if we then call that function, right, with 2, for example, then we will get back 3, right? So that thing will be equal to 3. But the type of the thing, if I only apply it to 1, right, and not to 2, that thing will be a function. And of course, notice here that we have this different syntax then, where we have, like, we're calling the function, we're applying it to some argument, and then we're closing that, and then we're opening again, and then we're calling it with the next argument. So I can't call it like this, right, with a comma, because it's no longer like f, or actually, like, concretely, let me remove this stuff. So, like, concretely, the function add, if I define it with this upper type signature, it isn't anymore a two-arity function or a binary function. It's actually a unary function initially, which means it doesn't matter if I say add 1, 2, right? Only this first variable will actually be used, only this first argument, right? In a language like JavaScript. In a language like well, I don't know, I mean, like, whatever. I mean, if you have a statically typed language, like, let's say C#, and you try to pass 2 arguments to a function that expects 1 argument, then of course you'll get a compiler error. Like, they'll just say, like, you can't do this. Now, that's in some sense, so we have to call it like this, right? And that's no problem, right? Like, if you're doing functional programming in JavaScript, and you're not using any external libraries, then you might be working like this. And I'd say that's totally fine. Like, that's purely syntactical. It's just like, it doesn't really matter whether we do this or whether we have this comma, right? It's like, it's a convenience to use this comma syntax, but the power of currying is too great, or the power of partial application is too great, so it's worth giving up this other syntax. But anyways, you can also define, you can also curry, you can also sort of auto-curry multiarity functions, or I'm sort of hand-waving now, or sort of define multiple versions of the same function that's not really what I mean, but like you can, okay, what I mean is that you can make your functions deal with both this way of invoking them and this way of invoking them. So if you're using a library such as, for example, Ramda, then they will have this function called autocurry, and they will, so that you can autocurry any multiarity function that you have, but they also autocurry every function in the library, which means that every function in their library can be called with any of these two syntaxes, like they're equivalent. One is just syntactic sugar for the other one. But okay, we're kind of off topic now. We need to get back to type definitions, right? So this is sort of currying and partial application. Again, don't sort of freak out if that makes no sense. Just look up a bit more on currying and partial application on YouTube, and then get back to this discussion, and I think that will make a ton of sense. It's essentially, again, about the decision as to whether you have a function that takes multiple arguments and then returns a result, or whether you have a function that takes only a single argument and then gives you back a new function that takes the next argument and then gives you back the result, right? And that series could, of course, continue indefinitely. I mean, indefinitely would make no sense, but maybe, yeah, it doesn't really matter. It can continue like in any length. So it's like you can have, let's say if you define a function which is if-else, right? Then you might have like an if function, first argument, an else function, a condition function, first argument, if true function, second argument, and an if false function, third argument, right? So then you have a ternary function, like a its arity is 3. It takes 3 arguments, right? And if again, like, so you might have this function if else, and if you call it, do you call it with this, like x, or like this, x, y, comma, z, like x, comma, y, comma, z, or do you call it like this, else x, y, z, right? If you call it like this, then it's a curried function, and you're performing partial application here, and then here it's fully applied. But here, in this uppercase, then, or in this above example, then you just have a multiarity function, or a function with an arity of 3. So that's essentially like the idea of currying versus partial application. But anyways, let's move on from this. Okay, so I just wanted to give an example of like what is a type signature, like what might that look like? Now let's actually talk more about let's talk about sets, right? So what is a function in some sense? So when we were defining this add function, we were saying that it maps from, let's say something like, let's define a yeah, because it's easier now if we have a unary function, so a function that takes a single argument, right? Because then we don't have to worry about this currying versus multiarity functions, right? Or curried functions versus multiarity functions. So let's instead talk about the function. Let's say that we have a function called inc, right? This function inc is a function. It's called inc. It takes, let's say, an integer, and then it maps to another integer, let's say, right? That's our type definition, or type signature. And what's the implementation? Let's again use JavaScript, right? Just as an example. So let's say const inc, the function is called inc. Of course, with inc, I mean increment, right? That's why I'm calling it inc. And its definition might be something like this. You get an x, and then you return x plus 1. Sorry, I just realized I should, as a note to the last, let me just draw a line here to say this stuff that I'm going to talk about now belongs to the last discussion before I wipe the board. What I should have said is that we defined add like this. Const add is a function, no, sorry, no, I'm mixing. Const add is a function that takes an x and a y and returns x plus y, right? That's the way we define add. But and that's the sort of multiarity version of add. Here's the sort of the fact that we have 2 arguments, right? If you defined it in a curried fashion, then you would define it like this. You would say const add is a function that takes an x, returns a new function that takes a y, and then returns the value of computing x plus y, right? That's completely valid JavaScript, right? That's a way of defining a curried function in JavaScript. Like instead of specifying multiple arguments, you simply just specify a series of returning the next function, and then in the end doing the computation that you're actually interested in, right? So the difference is really here, right? Here, this versus this. Those are the two things you should compare, right? This is curried, which allows for partial application, and this is like, let's say, multi-arity. I don't know if that's like a sensible term for that or not, but I think you see what I mean, right? Taking multiple arguments versus taking a series of single arguments-ish. I was strangely put, but whatever. That was part of the last discussion. I should have said that so that you've seen sort of what it might look like in JavaScript if we implement a curried function which is partially applicable. Okay, but now let's say we have this type definition. Let's say we have a type definition for a function called inc. It maps from int to int. So when given an int, it will give you back a new int, right? And not just any int, right? Like if we look at the, I mean, okay, from the type signatures point of view, we don't know, right? Like we have zero idea what this, what the implementation of this thing is. Of course, right? That's the point of a type signature. You can specify something which is very general, right? And I'll get back to this in a moment, right? But the actual implementation that we have is that it's again, it's called inc, short for increment. And what we're doing is that we're taking some x, and then we're simply adding 1 to that x, so we're returning that, right? So obviously, if I call inc on 2, we get back 3. If I call inc on 4, we get back 5, and so forth, right? If we if we call it with n, we get back n plus 1. Okay, obviously. Now, what was I going to talk about? Ah, sets. Okay, sorry. So sets. So what does this actually mean? Like, what does this mapping from int to int actually mean, right? So in order in order to talk about that, we have to talk a bit about functions in mathematics, or I don't know, potentially category theory. Again, like I'm not formally schooled, so bear with me if I'm saying this incorrectly. But you can think of this as two sets, which now actually are the same set because we're mapping from int to int, but yeah, I just have two representations of exactly the same thing. Like, I mean, the thing about sets, right? When we talk about sets, we're talking about things that are used, such as in for example, Venn diagrams, like, right? Like when you're saying, like, I don't know, like every, yeah, whatever. I mean, it's like, every programming okay, I should have thought about an example, right? Like a set can be any collection of a number of things, like hypothetical. Like you could say the set of all programming languages, right? Like the collection of all programming languages that we can think, that say currently exist. Like that's the definition of a set. But then we could say like the set of all object-oriented programming languages, right? So maybe you could say something like that. You could say like all dynamic, like the set of all dynamically typed languages. Let's say this is the set of all dynamically typed languages, dynamically typed programming languages, and then maybe this is the set of all functional programming languages, right? And obviously then there's some overlap in between, like there's some intersection between them, but there's also some stuff that's specific to that. Like, so Python, for example, would be here, right? Because, okay, maybe people would argue that Python is functional. Let's just, like, for the sake of argument, let's say that Python is originally, let's say, object-oriented-ish, like, or pragmatically object-oriented. Then Python would be here, right? Python. It's a dynamically typed language, but it's not a functional language, which means it's not here. It's obviously not here because it's not a... and it's not here because it's not a functional language, but it's here because it's dynamically typed. Whereas JavaScript would be here in this intersection, right? It's a dynamically typed language that's also a functional language. Let's say, I mean, for the sake of argument, let's drop the argument of whether my representations of these languages are actually correct or not, right? But this is the way we use sets, right? So it's like, you can say, let's say, the set of all mammals and the set of all things that have 2 legs, let's say, right? And so a human being would be in the intersection between those two. But you might have, yeah, so birds, for example, some birds that lay eggs are not mammals, but they have 2 legs. Oh, sorry. Okay, and this is just a set, right? It's like a collection of things, like and you can define this in absolutely any way you would like, right? Which is useful for you. And when we talk about sets in terms of type signatures, then we're talking about types, right? So I mean, think about it. What are types, right? Types are like int is a type, right? Float is a type. String is a type. Anything you define yourself, like a class that you define yourself in an object-oriented language, right? Animal is a class and hence a type. User is a potential class and a potential type, right? So it's like anything that you can think of could potentially become a type if you define it as a type, right? And so that's what we mean when we're talking about sort of types here, and it's very useful to think of them as sets. Now, my understanding is that if you get into category theory, for example, and then you start to do this kind of analysis, then you can no longer talk about sets, because sets are not categories. But whew, I mean, this is like, it's over my head, and I don't think it's relevant to actually pragmatically understanding how to read and construct type signatures. Now, if you want to get into category theory, of course, then you have to understand it. But that's, I mean, let's do that later. So what is the function inc, right? So if we define the function inc, then that can be described as the mapping of elements in this terminology, in this domain, which is the set of int, or the set of all integers, to the codomain, which is the set of all, which is also the set of all ints, right? So it's actually like, it's mapping from itself, right? So you can actually, like what I'm going to do is I'm going to draw arrows like this, like this, right? And of course, I mean, you could draw it any way you want, but whatever, like, but actually I could have drawn it maybe like this because it's the same set. I could have said something like this, like, I don't know, like not recursively, but like way back into the same type. But generally we tend to draw functions like this, right? So we're going to stick to that, right? So what I mean is this, like if you look at like this set here, the domain of the function inc is the set of all ints. So in other words, every int is a legal input value to the function inc. That's what we're saying, right? If you can construct an int, that's what we're saying when we're saying that the first argument to the function, the first argument to the function int is, the first argument to the function inc is an int, then that means that if you can construct an int, why did I choose two things that are so similar, right? If you can construct an integer, then that integer must, by definition, right? By definition, because we're saying that that's the type of the function is that it accepts an integer, then by definition, it must be a valid input to that function, right? And what we also know is that that integer must necessarily map to another integer in the codomain, right? Or yeah, in the codomain. And actually, like, then we also have this further complication of like within the codomain there's the image. So this is the image. And that just means, we're going to talk about this in a moment, but that just means that you might, like, even if something is a, even if you're describing the output type of a function in terms of a particular set, it might not actually be possible to get out values, to get out every possible value from that set through your function. So think about, let's define another function, right? Let's, how am I gonna do this in terms of space? Let's say, let's do something like this, right? Let's say you have a function called hello. Hello is a function that takes a string and returns a string, right? So let's say that the implementation of hello is a function that takes some s and then returns the string hello space plus yeah, I can put that on one line, plus s, right? So if I invoke the function and I send Christopher, I say hello and I pass Christopher, right? Then as a return value, I get back hello Christopher, right? And if you pass foo, you get hello foo. If you pass bar, you get hello bar, and so forth, right? So the point I'm trying to make is that this function, by definition, given the implementation of this function, necessarily it will always return hello and then that value, right? So in some sense then the image of that function is not actually the whole set of all possible strings, because you can't get all possible strings out of it. Like you can't, like it's impossible to from that function get the string Christopher. It's impossible, like no matter what you pass it, you can't get Christopher, because you always will get a string back that starts with hello space. Always, right? Not because of the type definition, type declaration, but because of the implementation. Now, whether that constitutes a valid description of the concept of an image, I'm not entirely sure. That's the way I think about it, but maybe you have to say that the image has to be, let's say, defined, or you have to be able to determine what the image is on the type level. Maybe somebody can correct me on that in the comments in case I'm wrong, right? But yeah. So okay, so that was an example of an image, right? But generally, we just sort of need to think about the domain and the codomain. So let's sort of review, right? It's like it's kind of like we have now already defined this symbol and this symbol, right? Notice how we drew these originally in the beginning. We have that first symbol here, and then we have the second symbol here, and this symbol, this sort of double colon symbol, should be read as is a, or could be read as, maybe I should say, is a member of, right? So what we say is that the function called inc is a member of the set of functions, if we draw this sort of imaginary parenthesis here, the set of functions that when given an int will give you back a new function that maps, or sorry, that's for the binary function. What I meant is that given given an, okay, let me restart, sorry. Inc is a member of the set of all functions that map from integers to integers, right? And this is sort of, if you think about that, this is somewhere along these lines is sort of where it clicked for me in regards to functions as first-class citizens, right? Remember how some people draw the line. I mean, everybody has a different definition of what sort of constitutes a functional language, but I guess one of the requirements that make it, like, if you don't have that, it's very difficult to argue that something is a functional language. So if functions are not first-class citizens, which means that you can take a function, put it in a variable, and pass that variable around, right? If functions are not first-class citizens, then it's tricky to argue that that language is functional. But anyways, this is, when I understood this is sort of when it struck me that what this means, right? Like, how can a function be a value? Well, of course you could say that a function is something that maps from members of a set to members of another set, that maps from a domain to a codomain. So it's like, sorry, I should have drawn here as well. Like the domain in this case, like an element in the domain here would be, for example, 1. I'm just drawing a bunch of examples, right? Like these 4 arrows are just 4 example arrows, but of course the number of arrows here would, in theory, like in mathematical theory, be infinite. But in any programming language where you have a maximum size integer, it wouldn't actually be. I mean, it would be finite, it would not be infinite, but in theory it's infinite, right? So the number 1 in the domain would map to the number 2 in the codomain, more specifically in the image. The number 2 in the domain would map to the number 3 in the codomain. The number 3 in the domain would map to the number 4 in the codomain, and the number 4 in the domain would map to the number 5 in the codomain, right? Given the current implementation of inc. But, right? But if you put this into a set, not this, but if you put this, the idea of int to int, if you put that into a set, right? Then you could say, well, this is a set of all int to int functions. Then you can easily imagine, well, that's like an infinite set, because you can think of any number, like there's an infinite number of variations of functions that map from integers to integers. Another example is, for example, decrement, right? Let's define dec. So the type definition of dec would be that the function is called dec for decrement when given an int it returns an int. Clearly, right? But the implementation, I'm going to omit the word const now just to save space, like I did here for hello as well. But just imagine that I'm doing JavaScript, but I'm using the word const or let or var or whatever. But the implementation of dec would be this. Dec is a function that takes some x and returns x minus 1. Clearly, Clearly, decrementing is not the same thing as incrementing. Where is it? Here, incrementing, right? Obviously, they have different implementations, but on the type level, they're exactly the same. Right? I mean, they're not exactly the same. Sorry, or maybe, yeah. They're members, like both implementations are members of the same set on the type level. So that means that decrement and increment are substitutable functions, right? And this is how you can sort of think that they're first-class citizens, right? It's like if you declare, right? If you declare that I have a variable called inc and it contains something that maps from int to int, right? Then you can actually put the function decrement in that variable, and that's totally fine, because that has the same type signature. But you can also put the increment function in that. And that's like, by analogy, think about that. That sort of means the same thing as that when you define, let's say you declare in an object-oriented language or a procedural language, you declare an integer. You say, I have an int, and I call it a. Then you say equals, and then you specify a literal, right? And then you say int a equals 5, or 2, or like 145, or whatever, right? It doesn't matter what you actually put in that variable, right? And it's the same thing in a functional language. It's like you just define that I declare that I have this thing that follows a particular type. I have this thing that maps from some domain to some codomain. It maps from some input type to some output type. And that's the type of the function, right? And then you can put any implementation that satisfies that type signature in that variable. Pretty cool stuff. In my mind, that sounds like pretty cool stuff. And this is sort of, at least for me, this is sort of when it started to click how we should think about approaching functional programming. Like, what does it mean to have a function as a first-class citizen? But anyways, let's keep moving, right? And I sort of don't want to go too far in this, but I mean, if you think about a curried function, right? If you think about a function that has this, like now we talk about unary functions because it's simpler, right? We talked about the function hello that takes a string and yields a string, or maps to a string, like from a string, or the functions increment and decrement that take integers and map to integers. But if you have something like add, for example, let's remove this and draw up add. So if you have something. So now I'm sort of on a bit of shaky ground, but I'll try to keep my head straight. So if you have a function like add that, like in the curried sense, that maps from int to int to int. Now, what would that mean in terms of domains and codomains? So that means that the function add, right, is a function that maps from the set int to the set int. Or sorry, from the set int to the set of int to int functions. This is the way I understand it. Maybe, I mean, correct me if I'm wrong, right? But this just seems like the logical way to read this, right? It's like add is a function that when you pass it a number, right? When you call add on 5, then you will get back a new function that, depending on what value you pass it later, it will give you another output. Like, what I mean is, if you call add on 5 and then on 10, then of course you will get back 15, right? But if you think about it this way, if we pass 1 here in the beginning, then we will get back 11, and actually that means that in the set of it's mapping from its domain of integers to its codomain, domain of int to int mappers, of int to int functions. So that means that if you call this add 1, like if we look at only this first step, only applying it to its first argument, then the function that we will get back in the codomain is actually the function inc, right? And interestingly, if we call it with -1, then we will get back the function dec, right? And this is the power of partial application, right? Or currying. So you can partially apply stuff, get back a new function, and tons of times you don't have to write new functions. You can just write your new functions as partial applications of already existing more general functions. That's sort of like currying and composition. Fantastic stuff, right? But this is another video. Let's talk about that some other time. But I think this, if you think about this for a moment, that sort of helps to understand what goes on with partial application, and also how to think about a sort of multiarity function, right? In like well, if it just takes an int, I mean, it's like, if I look at this whole thing at once, it's like, well, how do I draw this? Do I draw this sort of like this with like 3 sets or something like that? Like maybe you could draw it that way, right? But it's probably easier just to think about it this way. It's like you take one argument at a time. You just take this first integer, and then you sort of parenthesize the rest. And then you say, okay, well, if I pass it the first integer, I'm going to get back a function that does the rest of the things, right? And if I then pass it another integer, if I draw the parenthesis here, oops, here actually, let's say, then I'll just, well, that makes no sense, sorry. What I meant is that if we only consider the first integer, right, then I'll get back this thing. I'll get back something from the set of int to int mappers, of functions that map from integers to integers. But if I then pass an integer to that function, this integer, then I'll simply get back an integer, right? So in some sense, it doesn't matter whether you have like something that maps from some type A to some type B, or in the case of int to int, from type A to A, or if you have an A, right? It doesn't matter if you have an int or if you have something that maps from int to int. Like, both are values and both can be passed around. And this is sort of what it means for functions to be first-class citizens. Anyways, let's keep going. So this is maybe just one way of thinking about sort of this like a curried multiarity function, or it's like a curried function essentially. But let's keep moving, right? So we've talked about this symbol, right? This sort of means is a member. Let's just say member of, like member, and like I say member of a set, even though that's probably technically wrong. But I mean, who cares? It's like it helps to understand what we mean here. It's like it's a when I say, so I mean, we could say this, for example, right? It's like how to do, yeah, so let's say this, right? I mean, it's like, what did we call the variable before A, right? Okay, maybe that was A is commonly used in types for Haskell, so let's not use that, but let's say n, right? So I've got the variable n, and it's a member of the set int. So now I don't have a function, right? I have a number, right? The set of ints, right? It could be like 5, 10, 365, whatever, right? It's some value from that set. But then you might have the set of int to int mappers, again, right? Like a bunch of functions, such as the increment function, such as the decrement function, such as the sort of double function, such as the multiply with 365 function, or whatever, right? Like a bunch of functions that yield integers, or multiplication might be in there, right? Or sorry, no, the multiplication might not be in there, because multiplication is a two-arity function. But here we're talking about unary functions that map from int to int. So n is, so we're just saying here n is a member of int, but we could have said like f, just a variable name, is a member of the set int to int. Right? So it's a function that maps from integers to integers, so then it's a member of this set, such as the increment function or the decrement function or whatever. Okay, let's drop this, right? Okay, so we've talked about this symbol, a member of. This symbol, I don't even know, like, what do people actually call this, right? It's like, like the cheat sheet that I have is some stuff from the Fantasyland specification, which is a specification for type classes for JavaScript. So like trying to find a way of achieving interoperability between different implementations of algebraic data types in JavaScript. But if that doesn't really mean anything to you, never mind, right? It doesn't matter. It's just at some point, if you're working with JavaScript and you're working with functional programming, you'll get into the Fantasyland specification. It's interesting, right? And definitely read it if you feel that it sounds intriguing. So they call it a function type constructor, right? I think let's just not make it any more complicated, right? It's probably formally called a function type constructor. I just think of this symbol as maps to, right? It's also because I used a lot of LaTeX and LaTeX, right, for typesetting. And when you want to make this symbol in LaTeX, you call the command maps to, or you invoke the command maps to. But anyways, this symbol we've essentially used a lot of times, right? We've used it here. So it's sort of integral. It's like, and notice how I said maps to when we talked about that symbol. It's like I said, f is a function that maps elements from the set of integers to other elements, or potentially the same element in the set of integers. But of course, now we've only talked about int to int. It could of course have been, like, we could have had a type signature which is int to string, let's say, right? So that might be like to string for a number. So like I pass the number 5, and that would map me to the string representation of the number 5, for example, right? We're just saying hypothetically. So that's a sensible way of thinking about this symbol, maps to. What about this symbol? So this symbol is I don't really think it has an equivalent in a language such as Haskell, for example. I don't know about Scala, maybe I don't think Scala has, but I don't know enough about Scala. I virtually know nothing about Scala. But if you're in JavaScript, you might want this, right? And the reason we might want this is that it is a way of being able to talk about types, or like using type signatures when we have objects, like when we have objects that have functions. So if you have let's wipe this. So if you have a class, let's say, so now we get into two-arity functions, I guess. Like let's think of a class. What are we gonna say? Like, let's say person, maybe. Yeah, let's do the string example, right? So let's say that we have, I'm just gonna use pseudo syntax, right? Let me go black again. So let's say we have a class called person, and it has some constructor, constructor that takes some, let me say s, that'll be the name of the person, and then we'll assign this dot s to be this s that we were passed in. So let's say this is a person class that has some kind of name, and that's maybe I should call it name instead of s, right? So let's say this dot name is equal to the s that we were passing. So like we have instances of the class person that has names, like every person has names. And then we might have something like an instance method, let's call it greet, that takes, let's say, 0 arguments. Yeah, let's start with 0 arguments, and then we'll do with 1 argument, right? And maybe that returns, and then we'll do the same implementation that we had before, right? We'll just say hello space plus this dot name, right? So I think you can see sort of what this method in the class does. So notice that I'm trying to explicitly make a difference between methods and functions. So a function is something that doesn't reside on an object. It could if you have a module or whatever, but a method is something that resides on an object and somehow refers to this, right? I would think maybe if it doesn't refer to this, then it doesn't necessarily have to be considered a method. So I mean the keyword this, right? Something in its scope of the object, or the scope of the object, right? So if you have this class person, and we have this method greet, how do we define a type signature for greet? Because it's not what we did before, right? When we said, I can't remember, maybe we called it hello or something like that. But if we define greet as this, from string to string, right? That would be a valid type definition, but it's not a valid type definition for the method greet, right? Then we're defining greet as a function that takes a string and returns a string. It maps from string to string. That's not entirely true because the string is already in the context of the person instance. So that's when we use the squiggly arrow. So then we say greet is a function, or a method actually, and we're gonna need some more complications, but we're not gonna, I'm going to get into that in a moment, that maps from string, squiggly arrow, that's the most ugly squiggly arrow I've seen, like that, doesn't matter, whatever, that squiggly maps from string to string. Now this is totally a convention, right? I think it's a good convention. I mean, actually, in some sense, everything is convention, right? But this is the first time I came across the squiggly arrow was in the Fantasyland specification. I don't know, maybe it's used elsewhere, maybe it has a long history. Presumably it does, right? I don't know. Either way, it's a good idea. What they're saying is that this first string, right, what's to the left of the squiggly arrow is something that already exists within the instance that we're calling the greet method upon. So the existence of this squiggly arrow implies that this greet method is not a standalone function that we can just call. We can't just say greet and then pass some stuff, right? Instead, they're saying that greet is an instance method that resides on an object, so you need to have something of that type. Now, to do that, we need some more stuff. We need a constraint on type variables. So we need a type constraint because actually this isn't entirely valid. Like this syntax isn't entirely valid either. It's I guess a bit more valid, but it's still not entirely valid, right? And so what we need is that we need this symbol. So this symbol is type constraints. Type constraints. And it was unfortunate that I started sort of in this end where we now have to talk about type constraints at the same time that we have to talk about, let's say, what do we call this, like method? What do they call it in the Fantasyland specification? Yeah, they of course call it method type constructor. So method type constructor. Yeah, let me just say, like for the normal arrow, we'll just say quotation marks maps to, and then for the squiggly, we'll just say method quotation marks maps to. Okay. And then the question is, how do we rewrite this type declaration so that we're using the type constraints and the sort of the method maps to, right, the squiggly arrow, in a way that the Fantasyland specification wants us to use it. So what we have to do is that we have to do this. We have to say there is a method called greet, right? And the type of that method is that. Can you see this? Is it too far down? No, you can see this, cool. Is that assuming that there is an instance of the class called person, and I'll refer to that person, using the lowercase variable a here, right? So now we're actually also introducing this syntax, right? This syntax, I guess it's generic variables or something like that. What do they call it here? Constraints, Yeah, they're not using a name for it? Yeah, type variables, sorry, type variable. Yikes. Typing on a board, eh? Type variable. Okay. And I mean, we're using lowercase letters, so I happen to use A. Like conventionally, people tend to start from A and then go to B and C and D and so forth, but you could use any name. I mean, since we have a person here, you might want to use P because it's sort of representative, so you can remember that it's a person. But conventionally, people just start with A and then move onwards, right? So what we're saying is that we have to read this type of definition this way. Greet is a method that, or let's say, I mean, you could read this colon syntax as, yes, you can map it, read it as a member of, but if you want to sort of read out a type declaration, I think it's useful to read it as, sort of as such that, right? So then you could say greet is a method such that if you have a type variable called a that is of type person, right? That satisfies the type specification for person, then and then we use this sort of fat arrow, right? Notice that this is not the fat arrow in the JavaScript sense where we're actually implementing a function or a method, but it's this fat arrow, right? A type constraint. So this portion here is the type constraint, right? So we're saying that there's a type constraint on the type variable a. We're saying a is not free. A can't be anything. A has to be anything as long as it's a person. Like from the set of person, it could be anything in here. But it can't be anything outside of person. It can only be a person. Okay, so greet is a method such that if you have a person, and let's call that person A, if you then invoke the method greet, you will get back, or sorry, actually, if you pass no arguments, right, you will get back, let me make sure I get this right, you will get back a string, right? So if you invoke it, right, if you just call it without any arguments, you will get back a string. So this was kind of an unfortunate definition because now it's like we're saying, and now you can see how it becomes funny when we have instances, right? Because then suddenly we have this no arguments thing. Because like if you have an instance of something, and then any nullary function in that instance could actually be a unary function in sort of a non-object oriented sense, because that function or that method might actually read something from the scope of that person instance, which means that if you would extract it out and make it a function rather than a method, if you would make it something that's not an instance member of the class person, then it might have to be then it would have to be a unary function. It would have, like, if greet was defined as a standalone function, the definition would have to be this, right? It's something that maps from string to string. There's no like nullariness. There's no like this parenthesis parenthesis. There's nothing like, well, it doesn't take any arguments when we have sort of a standalone function. But when we have it as a, let me just remove this incorrect definition in the middle here. But when you have it as an instance method, then suddenly you get this sort of nullary behavior because you have it as an instance method. And it used to be, in its sort of general form, it used to be a unary function. If you have a binary function in a sort of general sense, or like it's not like a free sense, like a standalone sense, right? If you have let's say a greet by, let's say we have a greet by function that sort of takes one person and another person and then says like, it's like, hello Christopher, I'm John, or whatever, right? So you take two names and then you get back a string, for example, like we're just thinking about some hypothetical function. Then that's a binary function. That's a function that takes two arguments. Now we are not thinking about currying, right? We're saying that it's a binary function even though it's actually a series of unary functions, right? But like disregarding currying, then it's a binary function. But if you put that in the context of a person where one of the names actually belong to the instance person, or like to a person instance, then you've converted this binary function to a unary function, right? So it's like, if you make one of the variables, one of the arguments, an instance member, or an instance member of a class, then the arguments of the instance method will be n minus 1, right? It's like it will be 1 lower than if it was just a standalone function. Okay, that was sort of a side note, right? But this is actually a sensible syntax or a sensible definition of the method greet in the class person, right? So this is for a standalone. So let me just remove that, and let's add another one. Let's actually do something that, if it was a standalone function, would be binary, and then that in sort of as an instance method would be unary. So let's say maybe what is it, like let's say handshake or whatever, handshake, right? So let's say we get back some, or when we call the instance method handshake, we pass a string, which is this other person, right? And then maybe we return the string, let's say hello space plus s, the person that we've passed in, plus space, comma, I'm, and then space plus this dot name, right? So sorry, that just turns out a bit messy, but essentially what I'm trying to say is that the method handshake takes a string and then which is another person's name, and then simply just responds with hello, that person's name, I am, and then we print, or then we concatenate in our own name, right? So it's a mix of the name that we're being passed in as an argument and the name that I have as an instance member of my instance. So what would the type definition of that thing be? So the type definition of that thing would be this. Like we have greet here, and let's now define handshake. By the way, do pause the video and try this out on your own, and then restart and see if you got it right. It would be something like this: handshake. Handshake is a method such that, assuming that you have a person, and we will refer to this person as A, then if you pass, then if you pass a string, then you will get back a string. So hopefully that sort of makes sense, right? Let me just add also that if we define this handshake method as a function instead that didn't reside on the person instance, it would look something like this. The type definition or the type declaration would look something like this. So handshake is a member of the set of functions that map from string to string to string. Right? So notice how, like, in the standalone function, we actually have 3 mentions of the set of strings. But in the method version, we actually only have 2, right? We have the string that represents the other person's name here in the method signature, and here in the standalone signature, or in the function signature. And then we have the return string, like the string that actually is the hello message, and that's this string in the method, and that's this string in the function. But then in the function we have this string also, and like, where did this string go in the method? And that's this sort of weirdness with the fact that we have objects, that we're sort of mixing the 2 paradigms of object-oriented programming and functional programming, which is like cool and all that, but it's also a bit confusing when we get to type signatures. So that means that this string is implicit because it's hidden, quotation marks, within a person, right? It's like this method handshake no longer merely depends on you having a string, it actually depends on person, right? It's like it has a dependency on the idea of person. It means that to call the method handshake, you not only need a string, you also need an instance of a person in which there will be a string, but if we only look at this type signature, we don't know that, right? We just know that if you have a person and then you pass and you call the method handshake on the person and you pass it a string, you'll get back a string. Wait, sorry, did I actually draw? Oof, I drew this incorrectly, right? Oh, so bad. Yikes, my bad, dudes. Oof, 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 oof. Sorry, massive rewind. There's one tiny detail that I forgot here, and I sincerely apologize for going in one direction first and then realizing this is an error. Sorry, this is the way we should have drawn it. Let me write 2 of them at the same time, and then like I'll write the correct one for handshake, or actually I'll write the correct one for greet here, and then you can see person. So what I missed to draw is that we should have written it like this: greet is a method such that if you have a constraint on the variable A, or on the type variable A, such that A is of type person, right? And then we specify this arrow. I mean, you might have sort of gone like, wait a minute, but you said that you were going to use this sort of squiggly arrow, but we didn't actually ever use that squiggly arrow. And I sort of went too fast and I confused myself. So what we need to say then is that we first need to specify, given that, so this portion here, this portion doesn't actually say assuming that you have an a, right? It just says assuming that whenever you say the variable a, whenever you use the type variable a, you don't mean something that belongs to the set of all things, you mean something that belongs to the set of person, right? But it doesn't say that we have a person yet, right? This is just a type constraint. And then we have to say a, right? And that's when we're saying assuming that you have an a, and then squiggly arrow, and then same thing, parenthesis, parenthesis, and then string. So notice how if I remove this box, the thing that I missed when writing these two lower ones is this piece, right? Super important. This we also need to specify, right? And it seems like it doesn't matter in this case, because in this case it's actually, we can still understand it because there is nothing, like we're not actually using the a sort of in any sense, but in many scenarios you actually are, right? So that's why you would actually need you would need this separation, because you need to separate the type constraints from the from whatever happens after. And of course you could have multiple type constraints here as well, but let's not go into that now. Right? So let's rewrite the method handshake in this sense as well. So let me draw, or actually let's keep that. So the correct version of handshake would be this. Handshake is a method such that if when I say the type variable a, I mean something that belongs to the set of all person, of all people, right? Of anything. So I mean anything in the set of instances of people. And if I then if I then have such an a, and to the handshake method of that a, I'm passed a string, I will then get back a string, right? Sorry about that. So again, notice how the difference between these two things, or the difference between the correct version and the incorrect version, is that we needed to add this thing here, and here we needed to add, oops, sorry, here I need a squiggly arrow. Squiggly arrow. And I needed to add this thing here. Like that, right? So this version is incorrect, and this version is incorrect, right? But hopefully you're not super confused, right? Because there is only a minor difference between the two, between the correct versions and the incorrect versions, right? Like the incorrect version was that, or in the incorrect versions we were reading in too much from this sort of type constraint information. Now the type constraint information only sort of specifies type constraints. It only specifies, like, here's the type constraint, right? And here's the type constraint. It just says that from now on to the right of this, whenever I refer to a, I will mean something of type person, right? And same thing here. Whenever I say something of type a, I will mean something of type person. So yeah, that was the mistake. And then of course here you can see the squiggly arrow here and here. And the way we use that is that we're saying then, assuming that you have something of type A constrained down to person, right? So which in these contexts would mean that if assuming that you have something of type person, if you call the method which we've named here in the beginning, handshake or greet, and then you pass either here no arguments or here a string, you will in both cases get back a string. Okay, so let's try to wrap this up, right? We've defined the handshake as a function, sort of standalone function, and that's fine, right? Of course, there are lots of more stuff to this, right? I mean, in languages such as Haskell, you have very the opposite of primitive. You have very sophisticated type inference, and even in something like TypeScript, for example, for JavaScript, you have some level of type inference, not as cool as in Haskell, but I guess like PureScript also has type inference or stuff like that. So what I mean is that in Haskell, for example, if you would define the function, let's say, as we talked about before, let's say you define the function add. Or sorry, not like this. If it's Haskell, you define the function add that takes an x and then a y and is implemented as x plus y. Then Haskell will infer the type of this function. So you don't have to specify that add has the type, well, let's say int, for example. It's not actually going to be int, right? So this is a pretty stupid example. But anyways, I mean, it's not going to infer int for a number of different reasons, but let's not talk about them now. But add, it would infer something like int to int to int, right? Because like the first number, the second number, and the returned number. Probably it will actually, I mean, I don't really know this, but it would probably infer something like this rather. So this is actually a good way to talk about type variables and type constraints more generally, right? It might infer something like this. Add is a function that belongs to the set of functions that, given that when I say the variable type variable A, I mean something that belongs to the type class number. And you can think of type classes as interfaces in object-oriented programming. They're not exactly the same thing because it's part of, if I can't remember what that term is, right? But it's not object-oriented polymorphism, but it's ad hoc polymorphism. I'm thinking object-oriented polymorphism is actually specifically called something else, or like formally called something else. But we're talking about ad hoc polymorphism. So if you have a type class called num, it's like for numbers, and that's we refer to that thing as A. Then when given something of type A, given that when I say A, I refer to something of type num, or belonging to the type class num, then when given an A and then another A, I will get back an A, right? So this is sort of more generally how we can use type constraints. And this is sort of, when you start to get this stuff, then you can start to read all kinds of crazy type definitions, such as for functors or for monads or for monoids, because like you just have to identify, like, what's this piece? That's the type constraint. This is the type variable. This is the type class that they are sort of the set that they are binding the type variable to, or they're restricting the type variable to, such that so that it can't be anything, like anything from the world. This is the name of the function, and then here's a series of arguments that you get, right? Or like pass something of this type, pass something of that type, pass something of the next type, and then you get something back in the end. And think of these as sort of sets, like assuming that you get back something that belongs to this set. And then, of course, in something like JavaScript, or like in a semi-object-oriented world, you have something like the squiggly arrow, so you have to think about that as well, right? Like, what is the context in which this method is called? Like, what is the type of the thing that this method resides on? And here we talked about person, for example. So, I think I'm going to wrap this up here, right? Do watch through the videos, like skim through the different pieces more times if you feel that some of the pieces are confusing. But otherwise, please do shoot something in the comments and let me know what pieces of this are confusing, or what seems to not make sense to you. And then I can follow this video up with other videos, because if you don't say anything, I'm probably not going to make a follow-up video. But if you have some pieces which you would like me to explain in further detail, let me know and I'll make a follow-up video. Anyways, thanks a ton for watching. If you want more stuff like this, remember to subscribe to the channel, hit the like button if you appreciated this video, and I'll see you in the next one.